So during this second part, I will explain to you how we construct, how Christopher Gardiner, Humilier, Max Seyfaddini, and Smith constructed the link spectra invariants. So this relies on a really useful tool in symplectic geometry, which is called Floor homology. And in this case, so this is the Lagrangian flavor of this homology. So it's defined in the following way. We take a closed Lagrangian inside a closed symplectic manifold, so L inside M, and we pick a Hamiltonian function h from S1 times M to R. Then we will look at the set of smooth paths inside M that go from L to the image of L by phi h. So maybe let me draw a picture. So we have our Lagrangian. So we have our Lagrangian L. Its image phi h of L. And we're looking at the path that starts on L and go to phi h of L. We will choose a point x on L and look at its trajectory under the isotopy phi ht, and we will choose it as a reference path. So we have our point x here. We follow the isotopy, and of course we end up on phi h of L at time 1. And this path, we call it gamma. And we will look at the universal cover of the universal cover of this PL phi HL of the connected component of this reference path inside the set. So what does this mean? An element in there is a path from L to phi HL together with a homotopy of paths from the reference path to this one. So if I draw my picture, I had here a path so this is a path in P L phi HL. And I have my reference path here, and so my homotopy of paths will be what we call capping. So it has also boundary on L on the bottom and on phi HL. Oh, sorry, phi HL on top. Okay. Now we define an equivalence relation on this set. We say that so a path y together with a capping w is equivalent to another path y prime and a capping w prime if the two paths y and y prime are the same, and moreover the symplectic area of the two cappings agree. And we will define the set P to be the quotient of P tilde gamma by this equivalence relation. So now to define the floor homology, we will proceed as in Morse homology, for those of you who know what this is. We will define an action functional on the set P and look at its critical points. This will define as generators of the floor complex. And then we will look at the negative gradient flow lines of the action functional to define the differential on the complex. So in more details, we define the action functional by the following formula. The action of an element YW is equal to the integral of ht of x dt minus the symplectic area of the capping w. So here, this x, it does not depend on the point yw. This is the same x as we had before for the reference path. Yeah. So why do we add this constant to the action? It is so that it's more natural, because now if we change the reference path, like if we change the point x and the reference path, this will change this interval here, but it will also change the capping, since the capping goes from y to the reference path gamma. So if we change the reference path, we are moving this area, and we're also moving this integral here. And so one can, in fact, check that with this formula, both those changes will compensate each other. And so now this action will not depend on the choice of reference path. Okay, so as I said before, we want the generators of the Floer complex to be the critical points of this action functional. And one can check that this coincides with capped intersection points between L and phi h of L. So what I mean here is that if you have an intersection point between L and phi h L, this defines a constant path from L to phi h L. And then your generator is this point together with a capping from the reference path to this intersection point. So now to define the differential, we will need to look at the negative gradient of the action. And to do this, we need a Riemannian metric. So we will choose a family of almost complex structures JS on M that are compatible with omega. So maybe I should explain what this means. So an almost complex structure JS is an endomorphism of the tangent space of M, such that JS squared is equal to minus the identity. And compatible with omega means that if you define G of VW to be omega of JSVW, then this is a Riemannian metric. So given such an almost complex structure, we get a Riemannian metric on M. And by integrating this metric over paths, we get a metric on P. So this enables us to define something like a gradient for AH. And when we want to compute trajectories of the negative gradient, we end up with holomorphic JS holomorphic strips U from so from the strip R times 0, 1 to M, with one boundary on L and the other on phi HL. So I will draw what this is. So we have L, we have phi HL, and we have the strip. So this is, sorry, this is R times 0, 1. And we, so we have a map U that is JS holomorphic that maps this strip to a strip with the lower boundary here that is mapped to L, the top boundary that is mapped to phi h of L, and that is asymptotic to an intersection point y here and an intersection point y prime here. So this is the analog of a gradient flow line from a critical point of a Morse function to another critical point. So to define the differential on our complex, we will count such holomorphic strips. So for a relative homology class beta in H2 of M relative to L, we will define the moduli space of J holomorphic strips from Y to Y prime in class beta. Yeah, so we define by M beta JS Y prime the set of JS holomorphic strips from Y to Y prime in the class beta, mod out by the action of R by translation. So indeed, since the maps U go from R times 0, 1 to M, you can reparameterize here by translating the R coordinate, the R parameter. And this also yields JS holomorphic strip. And so we want to mod out by this equivalent relation by reparameterization. Now we claim, so this is an imported theorem by Fleur in the late 80s. He showed that if you take a generic choice of almost complex structure and Hamiltonian function, then this moduli space is a smooth manifold of dimension mu beta minus 1, where mu beta is what we call the Maslov index. So it only depends on the dimension depends on the homology class of the strip. In particular, when the Maslov index of beta is equal to 1, mu beta will be a dimension 0 manifold, and one can show that it is compact, so it has to be a finite collection of points. So we can count them and define the differential in the following way. So d of yw will be the sum of the count of strips from y to y prime in class beta times y prime w prime, where the sum is over all generators y prime w prime with w prime that can be written as the concatenation of the capping W plus the class beta, where beta has Maslov index 1. So this homology, so now that we have a differential, we check that its squares is equal to 0. So this is also really difficult result. To show this, you basically need to show that d squared will count, it's a sign count of boundary components of, of boundary points of one-dimensional compact manifold. And this uses really hard results by Gromov on the compactification of moduli spaces of holomorphic curves. So in the end, we get that d squared is equal to 0, and so we can define the homology of this complex. In the cases we will consider, so for the Lagrangian, we will always have that this floor homology is actually isomorphic to the singular homology of L, or Morse homology if you prefer. But this is not the case for all L. So for instance, if you take, say, you take the sphere, and you take a small circle inside your sphere here, then you can find a Hamiltonian diffeomorphism which will push this circle away from itself, somewhere there, for instance. And so you can see that there is no intersection point between L and phi h of L. So you have no generator in your floor complex, and so the homology is zero. In fact, when you can move L from itself, we say that L is displaceable by Hamiltonian diffeomorphisms. And for such a Lagrangian, you always have that HF star of L is equal to zero. But for us, this will not be the case. We will always have that the floor homology of L is isomorphic to its Morse homology. And remember, we had an action functional on the floor complex, which gives us filtration. So you can look at all critical points of the action functional of action less than lambda. This would generate a vector space CF less than lambda. And one can check that the differential D is action decreasing. Well, this is because the way we defined it, D was counting flow lines of the negative gradient of the action. And so when you end up at a point y prime from a point y, you've been following the negative gradient, so the action has to be lower at the end point than it was at the starting point. So therefore, the differential preserves the filtration, and so I mean it's action decreasing, so it defines its I mean the differential of an element in CF less than lambda is also of action less than lambda, and so we can so this gives us a subcomplex, and we can define its homology HF less than lambda. And then the inclusion map of I lambda from CF less than lambda to CF will induce a map in homology from HF less than lambda to HF. And from this filtration, we can define Lagrangian spectral invariant CL of H, which will be the infimum of lambda, such that the fundamental class of L will lie inside the image of I lambda. So when I say fundamental class, you see this isomorphism here is natural. So there is an element inside HF star L of H that I can call the fundamental class of L. And then this spectral invariance tells me the action at which I can already see, like the minimal action at which I can see a representative of the fundamental class. If some of you know about persistence homology, well, this is an example of persistence module. You have a filtration of your on your floor homology, and you can associate to it a barcode, and the spectral invariant is the endpoint of the semi-infinite bar representing the fundamental class. So this was the theory of Lagrangian spectral invariance. Now we want to do the same with our specific Lagrangian, which was a union of disjoint circles inside a disk. So we embedded the disk inside a sphere, and we had what we called an eta monotone Lagrangian link. So this meant that basically the areas of every connected component of the complement satisfied some equation between like involving the number of boundary component and this constant eta. So we want to define a spectral invariance using this Lagrangian. So one idea would be to take the product of the Li that lives in the Cartesian product sigma to the k. So here sigma is the sphere. So this is a Lagrangian submanifold, but as our circles were quite small, they have area lambda. So we had our sphere, and we had circles on the sphere. Each one of them can be displaced from itself. And so when you look at the product, you can displace L1 from itself inside the first sphere of the Cartesian product. And so this implies that the product L1 to Lk is displaceable, and therefore its floor homology is zero. So we will not be able to define a spectral invariant because there is no fundamental class. So what we do to solve this problem is we take the quotient of this Cartesian product by the permutation group Sk. And so we end up with a Lagrangian sim L inside the symmetric product of the sphere. And this time, this Lagrangian will not be displaceable, and one can check that its Floer homology will be isomorphic to its Morse homology, which in this case is the homology of a k-dimensional torus. Yeah, because it's a product of k circles. I say that this defines a Lagrangian submanifold inside the symmetric product, but actually it's not that easy because when you like there is a symplectic form on the symmetric product induced by the symplectic form on sigma to the k, but this symplectic form is not smooth on the diagonal delta. Sorry, I didn't define it. So delta is the set of points x1, xk, such that there exists two different indices with xi equal to xj. So it's the set of points in the symmetric product such that two of the coordinates are the same. So yes, so as I said, the symplectic form is not smooth near this diagonal, so we need to smooth it out. And we also need to deform the action functional to get non-zero homology. So this is done in more details in the paper of Christopher Gardiner, Humilier, Max Seyfaddini, and Smith. And so this deformation of the action here involves this parameter eta. So we had to subtract eta times the intersection product between the capping W and the diagonal. So then we can proceed, like we can compute Floer homology as I described before. Once we have shifted this, like deformed this action and and we have smoothened out the symplectic form, and we get a spectral invariant CL of H, which is defined as 1 over K. So this is just to normalize, times the standard Lagrangian spectral invariant of sim L inside the symmetric product of sigma of sim K of H. So yeah, and maybe I forgot to define sim K of H. Sim K of H is just, so it's Hamiltonian on a symmetric product. So it takes as an argument K points. And this is just the sum of HT xi over I. Okay, so this is how the spectral invariant was defined. And now with this, I can give you an idea of the proof of Morabito's result, where he, if you remember, he yeah, he showed that the difference of spectral invariance when you embed your link in two different spheres is proportional to the linking number of the braid defined by phi. So how did he prove that? Well, if you embed your disk into two different spheres and take a Hamiltonian H, you will get two different Floer complexes, but well, you have a natural correspondence between the generators of one and the other. Basically, the picture will look the same. It's just that you have changed the area of the component of the sphere that is not a disk. So you have this natural correspondence, and the only thing that changes now is the action of the generators. And you can see by the formula of the action that the action shift will depend on eta here. And it will be given by eta S1 minus eta S2 times the intersection product between W, the capping W, and delta. Then, if you take Hamiltonian diffeomorphism fixing the link L0, what is then a capping? So a capping is, if you remember, it's a homotopy from a reference path and an intersection point. But for the reference path, we took some x inside L. So here it's inside sim L. So this means we're picking one point xi inside each Li. And the reference path is just the trajectory of xi by the flow phi ht. And so you can see that this will define your braid. You have k strands starting at the xi, and this will define your braid that ends up on the same Lagrangian in the end, because phi is in the stabilizer. And so the capping W is a homotopy between this braid and a constant braid, which is just an intersection point between sim L and its image by phi. And so now the intersection product between W and the diagonal will correspond to times at which the strands of your braid will cross each other to go from your braid to the trivial braid. And one can check that this is exactly the definition of the linking number of braid, and therefore we get Morabito's theorem here. Thank you for your attention.